Okay, so we're going back to the derivative chart. I thought it would be good to make sure you pull your derivative chart of rules out. You're allowed to use this chart anytime you want. I have a fresh printout here, or almost fresh. I started to do a video a few minutes ago and I jumbled up on my words, so it's just a mess. So you have this filled out. In fact, you may even have a few of these filled out. I just want to go over these. If you have f of x is e to the x, the derivative of that, f prime of x, is going to be e to the x. But remember that if x is a function, then you're going to need to take the derivative of that function as part of the chain rule. So if you had e to the 2x, for example, then the derivative of that would be e to the 2x times 2, because 2 is the derivative of 2x. All right. So the next thing we have on the function, which on the sheet, which you might not have, I don't know that we covered this when we covered this, but f of x equals a to the x. So some function that has an exponent as x, but a is a value, regular numeric value instead of this special numeric value of e. We have just a to the x. So in this case, the derivative of a to the x is going to be a to the x, just like the e to the x part. But here we have to multiply this times ln of a. All right. Now, if x is a function of some type, we still have the chain rule again. So if we had something like a to the 2x, we'll do the same example. We're still going to have the derivative is going to be a to the 2x times ln of a times the derivative of 2x times 2. We would normally write the 2 out in front, actually. All right, but it works the same way as e to the x does. Okay, next rule, ln x. We know that the derivative of ln x is 1 over x. We know also that if this is a function, if x is a function here, instead of just x, we have to multiply this by the derivative of that function, so we have to apply the chain rule. So for example, if we had ln of 2x, the derivative there would be 1 over x times 2, which also would be 2 over x. So the derivative winds up in the numerator and x winds up in the denominator. Oh, I made a mistake with that. ln of 2x would be 1 over 2x times 2. So in that case, it actually cancels out when it's just a coefficient. When it's more complicated, you still have to follow the chain rule. Okay. Log base a to the x. Okay, now this is a different type of log function. It works kind of similarly if you look at the pattern here. F prime of x is going to equal 1 over x times ln of a. So notice it kind of looks a little bit like this. It's very related to that. Same thing applies here. If x is a function, we have to multiply by it. Let me make the function here, well, it winds up canceling out very often. Here, let's do this. Log of a of x squared. Now, in actuality, this x squared, you could pull this out in front as a 2 because of log rules, which is the next thing I'm going to go over. But let's just try to take it just as is. We would have 1 over x squared times ln of a times the derivative of x squared, which would be 2x. That 2x could go on the top. The x could cancel with the x squared. You can simplify it a little bit. All right. All right. Now, next thing I want to go over, I had a piece of paper here somewhere. I want to go over some log rules. Here's some log rules. It's a little review from Math 50. All right. Just to remind you what log rules are. These will come back to you. I guess I should also say that in this derivative rule stuff, we're going to deal a lot with e to the x, but not a lot with other values, and a lot with ln x, and not a whole lot with regular logs of other bases. All right. So log rules for Math 50. If you have two things in the argument being multiplied, you can split this up into two logs. Base stays the same. So if this was ln, in other words, log base e, if this was ln, we'd still have ln over here. Same thing would apply. So we have log base b of x plus log base b of y. So if we have multiplication inside the argument, we can split it up into two logs with a plus sign. Well, if multiplication means plus, division must mean, yes, subtraction. So log base b of x over y can also be re-expressed as log base b of x minus log base b of y. Now, all these rules will work in the opposite direction too. If you have a statement with addition in it and the bases are the same and the arguments are different, you can multiply the arguments and make one expression out of it. If you have subtraction, you can divide the arguments and make one expression out of it. Now, this is a fun one. When log base b of x is raised to a power, x is raised to power, not the whole function is raised to power. There's no parentheses here. This rule does not work with parentheses in this situation. It's just the argument x that's raised to a power. This can be re-expressed as y times log of base b of x. So the exponent of the argument can be pulled out in front as a coefficient. All right, the exponent of the argument can be pulled out in front as a coefficient. All right, that's another rule. Remember, this isn't derivatives, it's just review of log rules from last year. Now, this is another one. If we have a function with some type of a value in the argument and another value in the base, and we want a different base, we want a particular base. We'd like to work in base 10, for example. If this was a 7, this would get confusing. But we can rewrite this as a different base called the change of base rule. If we like 10s, we could use a 10 here, and we would have a up top. And then in the denominator, we would also use the same bases we used up here and with the b. So this base becomes the argument in the denominator. The argument of the original function becomes the argument in the numerator, and we can select whatever base we want. That also means we can change this to ln a over ln b. So if we like this use of natural logs, which we're going to like in calculus, anything that's some weird base we can change to an ln style function.